One of the biggest challenges in AI today isn't really about making models smarter, it's about making them smaller. So today, we're going to dive into the absolutely fascinating world of tiny machine learning, or TinyML for short.
And it all boils down to this one huge question. On one hand, you have these massive, incredibly powerful AI models that live in the cloud. And on the other, you have billions of tiny, low-powered devices all around us, in our homes, our cars, our offices. So how on earth do we cram the power of a data center onto a chip the size of a coin?
To give you an idea of the scale we're talking about, a pretty typical deep neural network can be enormous. We're talking something like a 240 megabyte file. That's kind of like trying to download a half-hour TV show onto a device that can barely hold a single photo. Now, let's compare that giant file to the hardware we're trying to run it on. A standard microcontroller has, well, let's just say, very limited resources. Just how limited are we talking about? You get about 1 megabyte of storage, and maybe, if you're lucky, 256 kilobytes of RAM. That difference is absolutely staggering. It's not just a challenge, it's like trying to fit an elephant into a shoebox. It just doesn't seem possible. So there you have it, a massive model on one side and a minuscule amount of space on the other. This fundamental mismatch is the entire reason the field of TinyML even exists. But what if I told you there's a way to solve this seemingly impossible problem? Well, there is. It's an entire field of technology called TinyML, and honestly, it's a complete game changer. So what is it exactly? Well, put simply, TinyML is the art and science of getting machine learning models to run on these tiny processors using an incredibly small amount of energy. We're talking about the milliwatt range here. That's so little power you could run a device for an entire year on a single coin battery. And the advantages are just huge. That super low power consumption means you can have always-on intelligence. And because all the data gets processed right there on the device, you get incredibly low latency and way better privacy. Your sensitive data never has to leave. And on top of all that, it's cheap and super reliable.
Okay, so how is any of this even possible? How do you shrink that 240 megabyte model down to size? Well, there's a kind of secret sauce, a core technique that makes it all work. It's a process called model quantization.
Now, the technical definition can sound a little intense, but the core idea is actually really simple. It's all about simplification. You take all the very precise, complex numbers inside a model, we call them 32-bit floating point numbers, and you convert them into much, much simpler 8-bit integers. And this is the perfect analogy to help you wrap your head around it. Think of the original big model as a digital photo with over 16 million colors. It's beautiful, it's incredibly detailed, but the file is huge. Quantization is like reducing that same photo down to just 256 colors. To your eye, it looks almost exactly the same, but the file size is suddenly 4 times smaller. That's the magic right there. Okay, so we get what quantization is, but how do you actually do it? Well, it turns out there are 2 main paths you can take to make your AI models tiny. The first method is called post-training quantization, or PTQ. And as the name suggests, you do this after the model has already been fully trained. The second is quantization-aware training, or QAT. With this one, you're actually simulating the effects of quantization during the training process itself. And this table lays out the trade-offs perfectly. As you can see, PTQ is much simpler and faster because you do it after training. But there's a catch. You might see a small drop in the model's accuracy. QAT, on the other hand, is definitely more complex, but the reward is huge. You get accuracy that's nearly identical to the original full-sized model.
So the rule of thumb here is pretty straightforward. If you need a quick and easy way to see if your model will work, go with PTQ. But if you're building a real product where accuracy is absolutely critical, you'll want to invest the extra time and effort into QAT.
All right, that's all the theory. But does this stuff actually hold up in the real world? Let's take a look at the results when these techniques are applied to some really well-known models. Now, I know what you're probably thinking, because this all sounds a little too good to be true, right? A model that's 4 times smaller, faster, and more efficient. So what's the catch? Surely simplifying the model this much has to hurt its performance, doesn't it? Well, the results might just shock you. This chart shows the accuracy of 3 popular models before and after quantization. And what you're seeing is stunning. The bars are practically identical. There's almost no drop in performance. The accuracy loss is so small, it's basically a rounding error. In fact, and get ready for this is the most surprising part. In one case, for the mobile NetV1 model, quantization didn't just maintain accuracy, it actually increased it by a tiny bit. Yeah, it's a small number, but it's powerful proof of just how incredibly effective this process is.
So let's just sum up the massive win here. Through quantization, we get a model that's 4 times smaller, runs faster, and uses way less power, all with virtually zero negative impact on how well it actually works. This is the breakthrough that makes TinyML possible.
And this really brings us to a final, big question to think about. When we can pack this much artificial intelligence into tiny, cheap devices that can run for years on a single battery, what does that future actually look like? What new things become possible when intelligence is truly, and I mean truly, everywhere?